Hello, I'm Oguzhan. I'm going to talk about adaptive priority mechanisms today, and this is joint work with Joel Flynn. The main question we have today is the authorities that are choosing allocation mechanisms, and these authorities are balancing two conflicting objectives. And these objectives for us is going to be efficiency and diversity. Let me talk a little bit more about what I mean by efficiency and diversity in our setting. We are thinking about settings where agents who are going to receive the resources are heterogeneous in two different domains. The first domain is what we call the quality domain, and the quality domain is parameterized by scores of the agent. So each agent will have a score, and the higher scores and the scores will give us the suitability of the agent to the resource. And higher scoring agents will be more suitable to the resource. The examples would be in a selective schools context, higher scoring agents, like agents with higher academic achievement will be higher scoring agents and will be more suitable to the object, which is seats at a selective school. Whereas in a medical resource allocation context, the scores can denote the index of clinical need of the patients, where higher scores will denote needier patients. And in this setting, the authority that's in charge of allocating the resource would like to allocate the resource to the most suitable agents, in other words, the highest scoring agents, and this is what we mean by efficiency in this setting. The second domain where agents are heterogeneous is the diversity domain, and each agent will have different socioeconomic characteristics, and the authority in charge of allocation would like to allocate the resource to a set of agents who represent a diverse set of the population. So they want them to have different socioeconomic characteristics. This is an important problem in many settings, and we see that the authorities in charge of resource allocation mainly use two primary policy tools. The first one is what we call priority subsidies, or priorities, and these policies give certain individuals in certain groups higher scores. So basically, you can think that everyone has their scores, but if you belong to a certain socioeconomic group, then you get some bonus points. And examples of this are the scoring system in how minorities get bonus points in the scoring system of University of Michigan's undergraduate admissions, or how disadvantaged students who belong to some disadvantaged groups in Vietnam get bonus points in university entrance exam. And there are many other examples. The second policy tool is what we call quotas, which basically reserves some portion of the resource for certain groups and then proceeds with the allocation, while those portions are only eligible to be allocated to individuals or agents that belong to those certain groups. The examples are how the school seats were reserved for students who live close to those schools in Boston Public Schools, or how the selective exam schools in Chicago divide the city to 4 different socioeconomic tiers and then allocate and reserve, I think, 60% of the school seats for people who belong to each socioeconomic tier, like 15 times 4, basically. The question we ask today is that when authorities trying to balance these two conflicting objectives, should they use a priority or a quota mechanism or an altogether alternative mechanism? To this end, we'll analyze an authority with separable preferences over these quality and diversity domains and faces uncertainty about the economy that they are going to do the resource allocation. An important caveat with this is that the preference of the authority over agents is endogenous in the setting, in the sense that the authority, whether the authority prefers to allocate the resource to individual I or individual J, depends on how many people already have the resource from socioeconomic group of I or socioeconomic group of J. And to my knowledge, this is the first time we see something like this in a continuum choice setting. But of course, there might be. And then this will create some complications about the existence of stable outcomes, which I will comment later. To this end, we introduce a new class of mechanisms, which we call adaptive priority mechanisms. And these mechanisms make agents' priorities depend on their own score, but on top of that, the admissions of their own group. As a result, these policies will be able to adapt the different realizations of uncertainty, different realizations of the state, and i.e. the uncertainty, and we derive a particular adaptive priority mechanism that achieves ex post optimal allocation in all states. Moreover, it depends only on the preferences of the authority and not the set of possible state or distribution over this of these states. In other words, this mechanism, this optimal ex post optimal mechanism would be robust to the beliefs that the authority has. These 3 bullet points are the things that I will be able to for sure show you today. We do 3 other important things in the paper, which at the end I will comment a little bit, and if I have time for the first one, I'll go into a little bit more detail. But what we do is that we ask the next question about the policies that are being used today, which are priority and quota policies, and characterize exactly when these policies are optimal and when these policies are suboptimal. We then extend the model to multiple authorities who are allocating resources. You can think this as a setting where different schools are allocating their seats. And we study the existence and uniqueness of stable allocation in that setting. And moreover, we think of a decentralized setting where agents apply to authorities sequentially and then show that the optimal adaptive priority mechanism that we derived in the single object setting is a dominant strategy for the schools to decide which students to admit. For the interest of time, I'll go very quickly over this incomplete literature list, but as you can imagine, we are contributing to the theory and design of matching markets, especially under affirmative action constraints, and then we'll use continuum models, so this will be another paper that is approaching the large matching markets from a continuum standpoint. So to begin with, I'll start with an example which we call priorities versus quotas, which is based on Weizmann's 1974 paper, prices versus quantities. In this example, the uncertainty, the utility functions, the distributions, everything will be parametric, and then we'll be able to get closed form solutions. And this will, as a result, hopefully this will make a good job in illustrating the resources. Then in the second section, I'll show that indeed these main ideas there is much more general and holds in very general models, and then I'll describe a little bit the extra results and conclude. So in the setting of our example, there is a single school with capacity Q and a continuum of students of measure greater than Q, of which measure kappa are minority students. All students prefer the school to their outside option, and minority students have scores that is uniformly distributed between 0 and 1. And this is like a very parametric and restrictive assumptions we make in this particular example. The majority students all have exactly score omega, and omega is distributed between omega lower bar and omega upper bar with distribution lambda. The authority's preferences are given by a function xi that takes into account 2 things. One is the quality domain, which is given by the total scores of admitted students. The second is the diversity domain, which for this setting depends on the measure of admitted minority students. And the preferences are given by this utility function that is additively separable in these domains, and moreover has the quadratic form, it has quadratic utility over the measure of admitted minority students, which takes the form x minus beta over 2x squared, where beta is the standard coefficient of risk aversion in quadratic utility. We will assume that parameters are such that there is interior affirmative action in all states. In this setting, an admissions policy returns the set of admitted students in each state of the world. And we consider 3 particular admissions policies. One is quotas, which first admits measure Q minority students in order of score, so admits highest scoring measure Q minority students, and then allocates rest of the capacity to all of the students according to their score. The second one is priorities, which increases the scores of minority students by alpha first, and then admit students in order of their transform scores. And these two are the policies that have been studied and used in the field. To define our proposed policy, I first define an adaptive priority policy, which is the function, which is the policy that assigns priority A of YS to a minority student with score S when measure Y of minority students are admitted. So your adaptive priority, if you are a minority student, depends not only on your score, but also the measure of admitted minority students. For this case, we will assume that this function is increasing in scores and decreasing in the measure. In the main model, I will show that this is actually, I'll get this as a result, but for this setting, just think that this is satisfied. An adaptive priority policy in this setting does nothing to the score of the majority student, and it's basically they have score S. An adaptive priority mechanism basically solves for S star such that if the minority student with score S star is the marginal applicant, the adaptive priority of this minority student is equal to the adaptive priority of the majority student, which is omega. And then here, kappa times Y minus S star is the measure of admitted minorities when the minority student S star and any other minority student who has higher score is admitted to or allocated the resource admitted to the school. And basically, this policy, this mechanism admits all minority students who has scores more than S star and allocates rest of the capacity to the majority students. In this setting, we consider the two questions. One is, what is the optimal mechanism? And two, we compare priority and quota policies and think about which one is better and when one dominates the other. We show that two statements are true. First is this particular adaptive priority mechanism that we characterize is first best optimal. So under every omega, it achieves the optimal allocation. And moreover, we solve for the optimal priority and quota mechanisms, which are much harder to solve compared to the optimal priority policy. And we show that the comparative advantage of priorities over quotas, which we denote by delta, is given by this form, which if you take a look, is scaled by the variance of omega, which is the extent of uncertainty of economy, but its sign is determined by 1 minus kappa beta. And as if you remember, beta is the degree of risk aversion of the mechanism designer, whereas kappa gives us the measure of minorities in every small interval, since we assume the distribution is uniform. So therefore, kappa is the sensitivity of the allocation, sensitivity of the diversity of the allocation to a priority policy. If kappa is very high, a very little bonus point changes the measure of minority students a lot, whereas kappa is low, the change is smaller. To see why these results are true, and to get intuition about this, first see that a quota of Q admits Q minority students in all states of the world. Whereas a priority policies introduce variability to the minority admissions, but positively select minority admissions across states of the world. This positive selection benefits as a level of benefit to the authority's utility, whereas this variability ends up being a cost for the authority. And then, therefore, we derive that priorities are preferred to quotas if and only if this inverse sensitivity, 1 over kappa, is larger than the risk aversion of the mechanism designer, or like the authority. As a result, we see that whether priorities should be used or quotas should be used, if we restrict attention to those two widely used policies, depends on the risk preferences of the mechanism designer and how sensitive the allocation, how sensitive the measures of admitted minorities to the small changes in scores. I'm not going to talk about that a lot today, but in the paper, we also show that this model is actually based on Weissman's 1974 paper, and we show that these trade-offs are exactly analogous to the trade-offs between prices and quantities when the government is regulating a firm. And the reason is that, like prices, priorities allow the resulting outcome to adapt to the state of the world to some extent, whereas quantities quantities discipline the outcome much more and basically depends on the relative risk preferences of the government and risk preferences of the authority in our setting. An adaptive priority policy manages to optimally balance this positive selection and guarantee effects. And to see why, if we go back and look at our utility function, we see that the derivative of this utility function with respect to the measure of minorities is 1 minus beta x. Therefore, the optimal adaptive priority policy simply takes the score of a minority student and gives an adaptive priority bonus, which exactly matches the marginal contribution of that student to the diversity utility of the authority. And the takeaway from this example is that 1, adaptive priority mechanisms are optimal, and 2, the trade-off between priority and quota mechanisms depends on the risk preferences of the mechanism designer. So now I can move to the main model and talk about optimal mechanisms with single authority. This will be much more general model, and we'll ask the same question in a much more general setting. And again, we assume measure Q, there is a measure Q of a single resource, and agents who are to be allocated the resource as modeled by theta, which tells us the score of the agent, which is denoted by S of theta, and the group of agent, the group the agent belongs, which is given by M of theta, where M is a finite set of possible groups that agent can be a member of. The set of states are denoted by omega, and there is a distribution lambda over omega, and the mechanism designer, the authority, does not know the economy they are facing when they are setting the rules of the game, the policies. In state omega, the economy is given by a measure f of omega over theta with density, with a density, and we assume that the measure of agents is larger than the measure of the resource to be allocated, because otherwise everyone gets the resource and everyone is happy. So to have the mechanism to have some level of bite. And then I guess the main point here is that at every omega, we have a continuum of agents, and the scores of these agents are distributed by these densities, conditional on their scores, conditional on their groups. And assignment mu is a mapping from the set of students to whether they are allocated the resource and they are not allocated the resource. And mathcal mu is the set of possible assignments. Whereas a mechanism takes the state of the economy to an assignment takes a state of the world to an assignment. And mu theta of omega is the assignment under the mechanism phi at state omega. The preferences of the authority that we are analyzing is similar to the first case and depends on 2 domains. First is the match quality, which is defined by a continuous and strictly increasing function h, which simply tells us the utility or the benefit the authority gets from allocating the resource to an agent who has score S. And the aggregate match quality is given by integrating with respect to the distribution omega in state omega, integrating with respect to the distribution omega, the set of agents who are assumed the resource, so this mu becomes 1, and the benefit of allocating the resource to those agents, basically. This is the aggregate match quality. The second domain is the measure of agents from each group who are allocated the resource, which is given by xm mu omega. We assume that the authority's preferences are given by the following Bernoulli utility function. For today, assume G is identity because I'm probably not be able to show the results where G matters. So as a result, the preferences are given by this function Xi, which is additively separable in these match quality, and diversity domains. And in the diversity domain, for the main results, we assume that it is again additively separable with respect to groups, where of XM gives us the utility the mechanism designer gets from allocating a measure XM of the resource to group M. We assume that this is a differentiable, concave, and weakly increasing for all M. But we don't need to assume this second additive separability between groups for the main results, and our results actually generalize with functional forms being different. So for example, let me quickly go over two example preferences. One would be an authority with affirmative action motives who prefers a particular group M to another group M prime. So the allocating a little bit more resource to group M is always better than allocating a little bit resource to group M prime. Whereas another example is an authority who prefers a balanced composition of allocated agents, which means that they don't differentiate between the groups. So basically, they are happy as long as all groups get the equal portion of the resource, but they dislike differences in terms of the percentages. In this setting, I am going to define what an adaptive priority mechanism is again, to match this more general setting. An adaptive priority policy is a set of functions, A, which for each group M, given the score of an agent and the measure of agent of the same group who are allocated the object, tells us the adaptive priority of that agent. So this depends, as the previous version depend on the version in the example depend on the measure of the admitted or allocated agents from the same group as well as the score. And I abused rotation a little bit. An adaptive priority mechanism, which is again based on these set of functions A, implements an assignment mu in state omega if the following are satisfied. One, the allocations must be in order of adapted priorities, which means that if type theta is allocated to the object, if and only if for all theta prime who are not allocated to the object, the adaptive priority of theta evaluated at matching mu needs to be larger than the adaptive priority of theta prime evaluated at matching mu. And this should be true for all theta who such that mu of theta equals 1. The second condition is the resource is fully allocated. And right now, we don't even know actually whether an APM actually implements an assignment or whether it implements multiple assignments. To this end, we say A is monotone when all these AM functions is a decreasing function of the measures and strictly increasing function of scores. So as I admit higher, like the A gives higher priority, adaptive priority to higher scoring students, and as it admits more and more students from a given group, conditional on scores, it reduces the adaptive priority. And we show that any monotone APM implements a unique allocation in the sense that all implemented allocations yield identical total scores and measures of admitted agents from each group. So there is only measure 0 differences, and monotone A's give us well-defined mechanisms. Yeah, now we can move to our main question, which is the optimality. And we say that a mechanism is first best optimal if attains the following value. What is this value? This is the expected utility the mechanism designer, the authority, gets under distribution omega. And then for this, we take the supremum over all phi. If a mechanism attains the supremum for all possible lambda, so for all possible distributions of states, we say that mechanism is first best optimal. A natural question here is that, is an optimal mechanism exist? And if so, what is it? And our main theorem shows that the following APM is monotone and first best optimal. So what does it look like? To get the intuition for it, assume H is identity function. Then A star takes the following form, S plus U prime of M, Ym, where type theta is awarded a subsidy of U prime M, Ym when there are Ym admitted agents from the same group. Basically, this equals this adaptive priority subsidy they get equals their direct marginal contribution to the diversity preferences of the authority when measure Ym of agents from their group is allocated the resource. And this precisely trades off the marginal benefit of additional diversity with the marginal cost of reduced match quality for the authority. Moreover, this A star can be requires only that the authority knows their preferences over match quality H and diversity UM, and can be fully specified even without any knowledge of the set of possible states and the extent of uncertainty. So in that sense, the optimality of the optimal APM is robust to the potential beliefs that the authority might have, whereas this is certainly not the case for the optimal priority or optimal quota policies. So I think I have 4 minutes. So in the 4 minutes, I'll quickly go over, describe the additional results we have in the paper. And the next and the most important result that we have is that we ask the following question. Now that we know what the optimal mechanism looks like, what about the mechanisms that are in use, namely priority and quota mechanisms? To this extent, we define 2 special cases of preferences of the authority. The first is risk neutrality, and risk neutrality is a case where all those UM functions are linear. So U prime M are constant, which corresponds to the setting where, in our example, beta equals 0, which is the coefficients of the risk aversion. The second thing we define is extreme risk aversion, which is an authority that has some target level of allocation, target level of admissions from each group, and loses a very high levels of utility if they fail to achieve that target level. In that setting, we show that priority mechanisms are optimal if and only if the authority is risk neutral, whereas quota mechanisms are optimal if and only if the authority is extremely risk averse, telling us that indeed the policies that have been used can be rationalized by some particular cases of preferences. However, there is also a very much more general set of preferences where the APM would provide a strict improvement to the mechanisms that are in use. Until this point, we only considered a single object and single authority. Now we extend, in the paper, we extend the model to multiple authorities. And we show the existence and uniqueness of a stable matching in a setting with multiple authorities. This is nice because we have a continuum model here where the preferences of the authorities over individuals are in some sense endogenous. And then indeed the adaptive priority mechanisms becomes instrumental in characterization of this stable matching. We show that APM are consistent with the unique stable matching in the sense that if any authority C is, or school C is looking at the set of students that weakly prefer that school to their match under the stable matching, they choose exactly the students that are matched to them in the stable matching. Finally, we go to a setting of a decentralized admission scheme where agents or students apply to the authorities, and authorities offer agents admission in a sequential way, in a decentralized admission scheme. Here we show that the optimal APM, which is A star, is a dominant strategy for all schools, which gives a non-cooperative foundation for the use of adaptive priority mechanisms, whereas we show that the allocation in all equilibria of this game, where the authorities use these dominant strategies, correspond to the unique stable matching of this economy, which gives a cooperative foundation to the use of APM in settings with multiple authorities. Let me skip the last bullet point. And to conclude, we analyzed a setting of an authority with separable preferences over quality and diversity domains, introduced adaptive priority mechanisms that showed that are ex post optimal in all states and robust to the beliefs of the mechanism designer or the authority. And we have these 3 additional results that I have just described. And thank you for listening, and I'll be here for any of the questions that you might have.
Do we have a marker?
So there's equivalence between then priorities and quotas, even if you take, I guess also if you take effort into consideration, right? That it shouldn't be a...
So the priority, without uncertainty, priorities or quotas are equivalent. It depends how you model uncertainty. Sorry, it depends how you model effort. Because if there is multiple equilibria in the effort state, then essentially there is uncertainty in the effort state. So then I'm not sure that the answer of that question is right. Yes. So that would confuse me.
Yeah. Any question?
So it strikes me like designing the priorities and quotas are sort of dual problems. Is there a way to think about the adaptive priority mechanism as sort of an adaptive quota mechanism where, say, the quotas start at 0 and you raise them by epsilon sort of greedily and then you arrive at the same result?
So I guess so, but what it would do would basically compute the allocation under the adaptive priority mechanism and match it with quotas. But they will be equivalent in this sense. Priorities and quotas are very different mechanisms, whereas adaptive priority mechanism achieves ex post optimality. So given that you know what an ex post optimal allocation is, you can have a mechanism that computes the quotas that matches the optimal APM's result. So that would be equivalent in my sense.
Thank you.
Okay.
So can you comment on why is there additive priority? Why it would not be multiplicative, for example? Because I can think of objectives where multiplicative priority might come up. Is this some functional form restriction, or it comes out of the proof that it must be additive?
Okay, good. It is driven by the preference assumptions we make, of course. So I try to stress as much as I can when I am talking about the preferences. The additive separability between score and diversity domains yields the additive nature of the optimal adaptive priority mechanism. But I think the additive separability in the preference of the mechanism designer is a very reasonable assumption, albeit it is not like universal, but I think quality and diversity domains are sufficiently apart from each other so that the preference of the designer is additively separable in both domains. Like it's a reasonable assumption, I would say, but you can think of cases where it will not be, but our paper or model does not cover those cases.
Okay, thank you again.
Yeah.
So next speaker, Fedor Sandomirsky from Caltech.